Good morning, everyone. Welcome to WESTalks. Today is the 10th week of the winter semester for us. And for people who are joining for the first time, IC Impacts is a pan-Canada, Canada-India Center of Excellence with international collaborations in the area of infrastructure, health, and water. And UBC Future Waters is an excellence body at UBC which focuses on interdisciplinary research at the intersection of law, policy, and governance. So WESTalks is a collaborative initiative brought together by IC Impacts and UBC Future Waters. And the organizing committee is basically Abhishek, Lady, myself, Carl, and Jaskaran. So we have graduate students from UBC as well as University of Guelph. Lady is a postdoctoral candidate, postdoctoral researcher here at UBC, and Feria is the IC Impacts supporter for us. So, welcome to the 10th week. Today we have Dr. Linda from Eawag. She'll be giving a talk on fecal sludge management. And we have talks even after April 8th, so you'll probably be notified if you have registered for our talks. And just to give you a snapshot of where we are today, so this was a snapshot taken yesterday. So that's the global outreach of WESTalks. And Carl would probably be sharing. If you're joining for the first time, please register on the link so that we can put your data on the sheet and then look at the global outreach of our WESTalks. And also, if you have missed any of our previous talks or you're interested in looking at any of our past talks, they are all available on YouTube at the IC Impacts YouTube page. With that, I'll welcome Dr. Linda. Dr. Linda leads a research group at Eawag in Sandec. So Sandec is basically the Department of Sanitary Engineering at Eawag. Her research focus is globally relevant solutions for sustainable citywide sanitation throughout developing fundamental scientific knowledge, translating it to innovative technology solutions, and ensuring uptake through implementation strategies. Her current research includes governing mechanism, controlling dewaterability, affordable methods for characterization and quantification, optimization of treatment techniques, and innovation in resource recovery. She's a founding member of SFT Promotion Initiative and FSM conferences, a contributor to the WHO Guidelines of Sanitation and Health, World Bank FSM tools, and editor at IWA publication journals such as Fecal Sludge Management, Systems Approach for Implementation and Approach, and Methods of Fecal Sludge Analysis. Her wide-ranging international experiences have given her a global perspective and an ability to research and apply engineering fundamentals in complex interdisciplinary solutions. With that, I welcome Linda. Linda, you may start sharing your screen.
Great, you can see that okay? Okay, thank you very much for the opportunity to participate in the WESTalks seminar, and thank you to everyone for joining today. So my presentation is Innovations in Fecal Sludge Management. And as Suhar said, I'm joining you today from Switzerland. So behind me, you see the Morteratsch Glacier. Since my talk is specifically about fecal sludge, I think it's important to take a quick aside and define exactly what we mean by fecal sludge so that we're all on the same page. So when I move my mouse around, can you see that? Okay, great. So excreta we refer to as urine and feces. And fecal sludge and wastewater are both comprised of excreta, but also anything else that's put into the toilet. So the main difference is that fecal sludge is defined operationally as not being connected to the sewer, whereas wastewater is transported through the sewer to centralized treatment facilities. So the main difference is the service chain, where fecal sludge is collected, transported, treated, and then hopefully resource recovery or end use. The terminology can also be confusing because the word sludge is not standardized. So if you're just referring to sludge, it could mean many different things here, as you see in this tree, from types of wastewater sludge to different types of fecal sludge. In addition, terms such as pit latrine and septic tank are not standardized and vary widely based on the location. So what many people refer to as septic tanks are in reality more actually like cesspits, But in other cities, they could be actually more like holding tanks. So it's really important when you're talking about fecal sludge management to be very clear and to explain exactly what it is that you're referring to. We try to get people to avoid using overly general terms like pits or sludge. Great. So, on to my presentation. What I'm going to talk about today is where we started, where we've gone as a sector, but also illustrating that with examples from my research group and where we're going to. So, I find it very exciting that as students and postdocs, you're organizing the seminar series on diverse and global perspectives related to WASH. Because when I started graduate school at the University of Washington, Seattle, based on my personal experiences, I had a passion to study possibilities for globally relevant non-sewered sanitation. But at that time, opportunities and funding to study non-sewered sanitation were for the most part not available. And it was something that we mainly pursued in our free time. So instead, my thesis projects were on the use of biosolid sludge in forestry. Here you see me there digging sludge into the forest, and on the fate of estrogens in centralized sewer-based treatment facilities. And in the United States, even though 1/4 of the population was served by on-site sanitation, the US EPA did not acknowledge that it could be a sustainable option until 2003. And globally, access to basic sanitation was only incorporated into the Millennium Development Goals, Target 7C, after the World Summit on Sustainable Development in Johannesburg, which was in 2002. So it modified the target to be having the proportion of people without sustainable access to safe drinking water and basic sanitation, they added. So in the 1980s and 90s, water and sanitation development projects in low-income countries were mainly focused on drinking water provision. So although these acknowledgments were made almost 20 years ago, until quite recently, non-sewered sanitation was still widely considered globally to be a temporary solution to bridge a gap until sewerage could be built. And even though in 2017, still over 1/3 of the world's population was served by non-sewered sanitation, and in low-income countries, less than 10% of areas were served by sewers. So on-site sanitation at that time was viewed as temporary holes in the ground that wasn't worthy of our attention or research or management, and engineers worked on sewer-based systems. And there were only a handful of universities that even had on-site sanitation in their curriculum. So many people at the university really thought it was crazy to give a shit about such a topic. However, there were some pioneers in different institutions who started already in the 80s and 90s to think about alternatives to sewerage sanitation for urban and peri-urban areas. And they played a key role in setting the path, and through knowledge sharing, education, and mentoring, helped to galvanize the field and build a critical mass of engineers, practitioners, and scientists working on sanitation. So I have to stress that in such a short presentation, there's no way I could acknowledge everyone, so I won't even try. But if you are interested in more history related to the development sector, this publication was just launched for World Water Day and explains a bit the international discourse on urban sanitation over the last years in the development sector. So I'm personally proud to be continuing the work of Strande at Eawag, who have been addressing sanitation needs in low and middle income countries since the early 1980s and fecal sludge management since the 1990s. And in 2009, Sandak published the first edition of the compendium. And in 2011, we started working on the first FSM book, the same year that the first FSM conference was held in Durban, South Africa, which with 120 participants, which has subsequently been growing exponentially. So then where have we gone to? Since the more widely recognized importance of sanitation, there has been a steady increase in commitment, uptake, implementation, and knowledge generation in non-sewered sanitation. And although it's never fast enough, views and attitudes are in fact changing quite quickly, and the necessity to consider non-grid small grid, and hybrid sanitation systems alongside sewage systems is globally gaining recognition. And one important driver has been the general increased public awareness, which can lead to change through political pressure. And this can be seen with popular press coverage of World Toilet Day, Bill Gates, this Indian film Toilet a Love Story, and this new book, Pipe Dreams. And I just wanted to add that to reduce overlap in my presentations with others that you've seen, I went through the list of your presentations and tried to cut out things that you've already had seminars on recently to avoid repetition. So this is an example where you can think about the global status of sanitation and the statistics about how it's changed, which I know you've also seen in other presentations recently. So where else have we gone to? There's been a rapid increase in evidence-based research and journal publications, and we're now able to obtain funding from national science foundations for our research. So that's really quite a change. And I can't stress the importance enough in continuing to fill the knowledge gap for practitioners and scientists to just get the existing information out there in a transparent fashion. So the experience that you have in your head is worth nothing to others if it's not shared. And much of the knowledge that we share today will become outdated, but in science, we don't generate facts. We generate knowledge and then improve upon it. And that's progress, and that's what we hope for. And also the recent shift towards open sharing of data is also an important driver in this. So we're all aware that technology alone is not the solution, and Barbara Evans also gave a presentation on that. But through solution-oriented research, there are rapidly evolving technology developments along the entire service chain. And some even have the potential to alter the existing service chain, such as container-based sanitation, decentralized options, and innovations developed through the Bill and Melinda Gates Foundation Reinvent the Toilet Challenge. And this includes examples such as hydrothermal carbonization, microwave technology, supercritical oxidation, pyrolysis, and electrochemical processes. And now off-grid solutions for Switzerland are being researched in the water hub at Nest, this building that you see here at Eawag, and we are actually informing the work on Blackwater based on our research experience in low-income countries. So I'm also going to leave out the collection and transport aspects of the service chain, as I know that Liz Tilley covered that already in her presentation specific to trash accumulation and on-site sanitation. But I do want to point out an important distinction of different places along the service chain where it's logical to quantify and characterize fecal sludge for monitoring it and management plans. So number one you see here is referring to excreta production. And there's a common misconception that excreta production is equivalent to fecal sludge production, but they're actually in fact quite different. Number two represents fecal sludge production, which is quite a bit larger because it also includes anything going into the toilet. So that includes washing materials and trash, but it could also be water from bathing or kitchen waste, water from the kitchen. And then number three here is representing what actually accumulates with time in the containment. And this is much, much lower than number two due to factors such as degradation, compression, and leaching out. So what I'm referring to here is what actually accumulates inside the containment, but it's also just as important to consider the fate of the liquid streams that are not contained. So for example, if you have a septic tank in an urban area, there's a huge difference between number two, everything that's going into it, versus number three, what's actually being contained inside the tank. Number four here is sludge that's emptied but not collected. Number five is sludge that is emptied, collected, but not delivered to treatment. And number six is what we want to see, where it's emptied, collected, transported to safe treatment. So moving along the service chain to what actually arrives at treatment, when you compare our scientific knowledge to the 100 plus years of research on activated sludge, we're really still in our infancy. And one important driver of research has been the acknowledgement that fecal sludge is quite different than wastewater and they cannot simply be co-treated together. So compared to previous knowledge, we've learned a lot about what fecal sludge actually is. And this figure here is illustrating the wide variation compared to wastewater. So what you see on the left is the Lubiji treatment plant in Kampala, Uganda. And at this treatment plant, they receive both wastewater and fecal sludge. The blue is representing the wastewater. So you can see the concentrations of fecal sludge can be much, much higher, but also much more variable. And they follow a much different distribution, which is also not a normal distribution. And the values on the figure on the right show the red dots as wastewater from the literature, and all of the other dots are examples of fecal sludge that have been reported. So quite different. And one reason for this is that the heterogeneity observed at the level of individual containments here is much greater with fecal sludge than wastewater, and also that heterogeneity is directly transferred to the treatment facilities, whereas with centralized sewers, it's relatively homogenized during the transport. So for the planning of management and treatment solutions, we need a way to average out this complexity so we can be able to make estimates at community to citywide scales for planning and management purposes. So methods are really lacking, and we see that because when treatment plants are built, they're frequently at commissioning almost immediately greatly over or under capacity. And this can be a risk to public health, but can also waste available resources. So we have been asking if we can use statistics to find categories of data that predict or separate out different ranges of characteristics and accumulation rates in order to average out this complexity and make reasonable projections. Excuse me, I'm super happy spring is here, but I'm suffering a bit with my allergy. So what if fecal sludge, for example, from households always had a higher total solids concentration? Or if septic tanks always had a lower total solids concentration? Could we use those categories of data for predictions? So we've been exploring whether categories of demographic, environmental, and technical categories of data could be used as predictors. So for example, income level is not a cause of why characteristics might be different, but there could be a correlation due to things like quality of construction or flows of wastewater going into containment, such as only toilets or also showers and kitchens. And this data here that you see is from Kampala, Uganda. The x-axis is these types of demographic, environmental, and technical data, and the y-axis is total solid. So you can see that many categories of these demographic, environmental, and technical data were statistically different, such as household, non-household, containment type, and income level. And we separated them based on these notches around the means that the medians that you see here, which we used since the data is non-normal. And with results like this, we could then use the total number of pit latrines and septic tanks in a whole community or city, or the number of people at each of the different income levels to extrapolate and make more accurate projections. So now we have over 1,000 data points in 8 different cities, and we're also using that to evaluate statistical relationships within the cities. So for example, you see in this graph here, the correlation between COD and total solids. And empirical observations like this could also be used to reduce analytical costs. So for example, total solids is pretty relatively easy and inexpensive to do in the laboratory, whereas COD requires more equipment and more chemicals. And we also observe lots of empirical relations like this when we're working with wastewater treatment. Also, we're looking at what trends we can see between multiple cities to see which knowledgeable is transferable among cities. So the figure here, you see emptying frequency in Hanoi and Kampala, and we evaluated a model to see if we could predict them with the same model in both cities. In our brand new book, Methods for Fecal Sludge Analysis, came out about 2 or 3 weeks ago. It's intended to start moving the sector towards more comparable results. And included in the book are background information on types of fecal sludge, methods for sampling, experimental designs for scaling up research, modeling approaches, synthetic recipes for research purposes, and laboratory methods currently in use by the partner labs. In addition, Chapter 5 here is an overview of the knowledge that we have developed over the last years around making citywide projections for quantities and qualities of fecal sludge. So the PDF of this book is available for no charge, for free. You can obtain it from our website, and in the coming months, it will be available for purchase from IWA. And in general, in Sandak, we try to make all of our publications available for free. So to get our research taken up as quickly as possible, we conduct a mix of applied, empirical, and fundamental forms of research. So we've been learning a lot about characteristics, but also treatment technologies. And the papers you see referred to here are from some of our applied and empirical research in dewatering technologies, such as planted and unted drying beds, and conditioners. And these research examples are in Cameroon, Senegal, Uganda, Vietnam, and Tanzania. So this research has been very important in adapting technologies for treatment of fecal sludge and improving operation. But in addition, we still need a deeper fundamental knowledge of treatment mechanisms and characteristics. An unpredictable dewatering performance remains a barrier to the effective management and treatment of fecal sludge. And this is currently the PhD research topic of BJ Ward and Stanley Sam in my group. So in this figure that you see here, you see the results of fecal sludge observed in this study in comparison to a conceptual model of our understanding of EPS and dewaterability of wastewater sludges. So in this paper, BJ demonstrated that fecal sludge with higher concentrations of EPS had higher comparable dewatering behavior and EPS content to aerobically digested in primary wastewater sludges. So that's what you see here, that in these studies, there were some sludges that had higher concentrations and they were more similar to wastewater. However, the lower EPS fecal sludges had different dewatering behavior than the wastewater sludges. So it appears that EPS explains partly the dewatering performance, but not entirely. And with fecal sludge, other mechanisms than in wastewater may be more significantly governing the behavior that we observe. So we're currently evaluating roles of particle size, stabilization with changes during storage time and containment in microbial communities to try to understand that better. And as improved understanding of the fundamentals of treatment mechanisms will be the basis to develop new and improved treatment technologies and continue to adapt existing ones. So there's still, in general, globally, a huge need to build fecal sludge treatment facilities. But one problem is that when they are constructed, most of them are actually operating without adequate operational or laboratory capacity. So there's a need to develop monitoring possibilities with simple, easy to measure parameters. And as you saw with the influent data from Kampala, we also need to be able to dynamically operate treatment plants to account for these widely fluctuating loading. So in this study, we collected 420 samples in Lusaka, Zambia, and we analyzed them for characteristics, dewaterability or dewatering performance, and also took a picture of each one with a color correction card. And BJ then used that data to create machine learning models to predict characteristics based on the photos. And she's now working on making that into a smartphone app. So in Lusaka, we saw that supernatant color was the best predictor of settling efficiency and filtration time. EC was the best predictor of ammonium, and texture, we can extract that from the picture, texture data was the best predictor of total solids. So in the future, we would like to improve our knowledge of these types of empirical relationships through a global database based on the smartphone app and the pictures in order to be able to develop low cost and reliable field methods. And such data will not be as accurate as laboratory-based methods, but depending on the application, could be accurate enough. So for example, with this first random forest model in Lusaka, if the total solids of influent sludge sample was 20 grams per liter, the model would currently predict it somewhere within a range of 7 to 33. So certainly for cases such as citywide planning or capacity of treatment facilities, this type of accuracy is good enough. So we're also sharing our raw data with our publications. With our two most recent publications, we've now shared almost 1,000 raw data points of characterization from Vietnam, Uganda, India, and Zambia. So that data is now available to anyone else in the whole world who also wants to explore and look for relationships. And as I said before, I just want to quickly reiterate that in the future, there's also a need to focus more on dealing with all fecal sludge streams and to not forget about the liquid streams or supernatants and gray water. In terms of resource recovery, as a sector, we have greatly expanded the possibilities, including energy as fuel and heat, food products such as animal fodder from plants, and protein production from black soldier flies, in addition to soil conditioners, fertilizers, and water reclamation. And these three publications here summarize our research, our applied research in resource recovery, and also provide help and guidelines and ways to select the optimal resource recovery based on potential markets for usage and also different types of technology requirements. In 2018, the WHO guidelines on sanitation and health were published, and among many other things, proposed technology levels of established, transferring, and emerging or innovative. And this is in order to develop risk management implementations to get the fastest possible uptake of emerging knowledge. So for example, solutions that are still at the level of innovative require much more support to ensure public health protection during implementations. So for example, maybe that's black soldier flies, in comparison to technologies that are more established, such as drying beds, where we are able to guide people in the design and operation much more reliably. So this concept is also explained in our online course, Introduction to Fecal Sludge Management. And also this highlights and exercises companion guide to the FSM book. And this concept has also been successfully implemented in Durban, South Africa, where they have a very strong university municipality relationship. So we need to continue to grow this approach to large-scale pilot research with research institutions working together with governments to scale up solutions. And that's because we just don't have the time to wait until technologies are fully developed before we start implementing solutions. Another important development, very importantly, has been curriculums have been and are continuing to now be developed and implemented. So now we have initiatives such as the Global Sanitation Graduate School and also freely available online courses. Here I gave the example of our Sandek MOOC series, which has now had over 160,000 online learners. And I also just want to point out that's also seen here today with the WESTalks. And the result is really an emerging new generation of students, practitioners, and scientists who will be the future champions in developing and implementing sanitation solutions. So from there, where are we going? A recognition of non-sewered sanitation has led to incorporation in development agendas, national regulations, government agendas, and implementations. And under the MDGs, sanitation was defined as household level access to a safe toilet. But recognition has led to a paradigm shift in thinking that building and counting toilets alone is not enough. And this is reflected in the Sustainable Development Goals, which include thinking of sanitation beyond access to toilets. And I know you've also heard about the SDGs in previous seminars. So universal access to sanitation is not an urban rural or rich poor question. And now instead of approaching sewered and non-sewered sanitation as separate solutions, we're talking about citywide inclusive sanitation that includes institutionalizing a service delivery approach along the entire service chain rather than just infrastructure provision. So, public health has now been brought into the conversation by considering entire neighborhoods and not only thinking at the household level. This is very important as there are clear links between fecal contamination together with population density on long term effects such as stunting, infant mortality, academic performance, and economic impacts. So, a number of initiatives have gotten us there, including public health aspects of safely and unsafely managed excreta. And this includes here the concept of the shit flow diagram, or the SFD, that was developed in 2012 as part of the World Bank funded 12 city study. Also, here are sanitation safety planning, which was developed by the World Health Organization, tools such as SaniPath, which was developed at Emory University, in addition to initiatives with business models and service provision. So we still have far to go, but I'm going to say if we're going to dream, then let's dream big. And let's shoot for governments that are talking about planning for combined solutions for water, sanitation, and solid waste, which are all intrinsically linked, with all of the services being essential for the protection of public and environmental health and also economic development. This will require a further paradigm shift, entailing more sophisticated planning, increased interagency cooperation, and government leadership and commitment. But by breaking these silos, we can help overcome the institutional barriers necessary to recognize the co-benefits of integrated approaches. So that concludes my presentation. And as I said, I just want to point out our URL here that all of our publications are available for free on our website. And so with that, now I would like to hear what questions you have for me.